This is Jim Hendershot. We're going to present to you lecture number 11, which is a lecture that covers the stator. The stators on these three machine types, some ideas and some criteria and some practices and requirements that you need to think ahead on before you begin your design of the stator. The stator requirements, as we said several times before, are very similar to one another for these three machine types: the induction motor, synchronous reluctance, and the permanent magnet synchronous machine. The cores must be made from low core loss soft magnetic materials, either laminated or sintered. We have to avoid saturation in the designs, in the teeth and the yoke cross sections. That means stay as close to the knee of the magnetization curve as possible. This means around between 1 and 1.4 Tesla. Try to avoid going up as high as 1.8. Now, thin tooth tips on the stator teeth. All these stators are open slot stators, and one of the problems with trying to use the same induction stator lamb with a PM machine is that those tooth tips saturate very quickly, which increases the cogging torque. So if there's any opportunity to change the die, the angles on the tooth tip should be increased so that the length of the tooth extension past the side of the tooth should be the same distance as the throat of the tooth where it attaches the tooth, to avoid saturation of tooth tips, which is like having a big slot opening. And when stacking the laminations into a core, avoid any interlamination shorts, and we'll discuss that further later in another lecture. But the laminations need to be insulated from each other through their entire surface, especially around the air gaps and at the OD. Otherwise, you get eddy currents there that cause very hot spots in the core, can short out windings. All kinds of horror stories have emerged. The cores should all be stacked from the individual lamination using precise tooling, and so that the cores are accurate. At some point, I'll show you a photograph of a poorly stacked rotor core for an induction motor, where the teeth are offset from each other, from one lamination next to the other, to such an extent that the cross-sectional area of the die-cast aluminum conductors is reduced a lot. This must be avoided, and your tooling should locate the lambs off of whatever's the most critical diameter. Maybe it's the teeth themselves, maybe it's the OD, maybe it's the ID. In the case of a brushless motor, it's probably the sides of the teeth or the OD. In the case of an induction motor, it's probably most important to locate the lambs off the ID, because the air gap's so small. The cores, in my opinion, after the core is completed, it must be stored to keep it from rusting, stored or wrapped in the outgassing anti-rust papers, or then after the core has been completed and insulated and wound and put in a motor, I think there should be encapsulated, painted, or dipped in varnish to keep it from rusting. These guidelines apply to axial flux stators as well, with a few modifications, but not many. Now, we always want to design a stator to produce a motor with maximum efficiency, so we want to minimize we want the frequencies to be low, the flux densities to be low, and it's desirable to punch a lamination from thin gauges of electrical steel with insulation core plates on at least one side. You can compare so that you can do the trade-off between the cost and the core losses. You can compare semi-processed materials with core plate on them versus laminations that have been annealed after they're punched, because the post-annealing costs money, but it certainly reduces the core losses. You could consider sintered electrical steel core components. That is really catching on in a lot of low-cost applications. And as long as your flux density requirements aren't too high, you can get very low core losses and have stator cores and rotor cores of very complicated shapes. These sintered parts don't have high tensile strength capabilities, so they have limited use in rotors, but they're very popular in high volume, low cost stators. There's another low core loss material called Met Glass. That's a trade name. That's an amorphous magnetic steel. It has a limitation on flux density of 1.54 Tesla, but very, very low core losses. So some cases that's hard to fabricate stators out of it, but that's something to consider. I think we mentioned that before. Minimize ohmic losses in the stator phase circuits. Use the largest wire diameter possible with the maximum slot fill possible, and minimize the phase coil end turn lengths. Keep the coil short. This is these are the two main issues that are the three main issues that are used to convert standard grid induction motors to high efficiency. That is to use better lamination materials with insulated coatings. Number one. Number two, higher slot fills. And number three, minimize end turn height. Those are the three strategies used to go to premium efficiency motors. And to optimize these strategies, it requires a careful balance between the copper space and the iron space. For if you're stuck with an existing lamination, the only thing you can modify, you can do two things. You can stuff it full of more copper by hand. You can shorten your end turns a bit, and you can increase the length of the machine a bit. That reduces both the flux density and the current density. As with respect to manufacturing the stator cores themselves, as we said, the laminations must be stacked using proper alignment fixtures, no matter whether by hand or automation, and they should always be stacked with the stamping burrs facing the same direction. Don't reverse the burrs. So they all need to be nested together with the burrs going the same direction. Stamping dies, they wear as they punch. Carbide dies don't wear as fast as tool steel dies, but they still wear, and the edges of the punch and the die get rounded off, and you get burrs that get wiped down the die clearance between the punch and the die. You get burrs on the lamb. So when those burrs get too big and get nested together and they're too large, they nest together very nicely, because when a lamination is stamped, it's sheared partway through its thickness, and then it's not sheared the rest of the way. It's a tear. It's torn, you might say, rather than sheared. So the sheared edge is not straight. It's right angles to the side of the laminations where it's sheared, but then it breaks away or tapers a bit where it tore, and that material that was torn becomes the burr. So the more slot clearance you have between the punch and the die, why the bigger the burr, and those burrs, when nested together, cause eddy current losses, shorting there. So at some point, when the burrs get too big, the dies have to be taken out and sharpened to reduce burrs again. So that's a manufacturing point that must be paid attention to and on your plant floor, and the designer should have some say-so and some in the process, not just to save money and wait longer till you sharpen the die, but to have a practice of sharpening it based on how big the burrs are. And if there's any misalignment of the lambs with respect to the slots, radial I mean, then that reduces your winding slot area. There shouldn't be any eccentricities between the ID and the OD from one lamb to the other. This is a problem too. If the alignment arbor is made too much smaller than the ID of the lamb, then the lambs are randomly located on that diameter. So so you wind up with a rotor or a stator that's much smaller in diameter than the punch lamination diameter, and that should be avoided. Expanding arbors should be used to locate lambs for stacking. It's very important. I've seen lots of lousy stacked cores. And when the cores are made, it's important to compress them under a high force at 90 degrees to the sides of the stack for squareness and flatness compression of the core. But before that core is cleated or welded, then that pressure should be dropped, so there's no compression stresses in the core. You need to compress it with a high force to get a good square stack and take care of any burr problems, and then release that pressure before the core is welded, TIG welded or laser welded on the OD. Never use filler metal when you weld a stator core. Either use TIG, plasma, or laser. And use several small welds, very narrow and not very deep, and put them over the center of a tooth. It's best to weld 180 degrees apart or all at the same time. If you have multiple torches and it's automated or semi-automated, make all the welds at the same time. Do not over weld cores. Never add filler metal, and you don't need any depression stamped in the laminations. A lot of people think you need a depressed place in the OD of the lamination to allow for the weld. That is not necessary. If you take laser or plasma, you'll never get any buildup of weld material. I know some people don't believe that, but it's absolutely true. It's not even arguable. You'll get some weld depressions from the shrinking of the weld, but you don't need to put a depression in there before you weld. You will not get any extruded weld materials as long as you start the arc off of the core. Start the arc, the laser or the TIG arc, off of the core on copper pieces on each end of the core. Now, but before you even have a core, you got to punch the laminations. So these are either done by laser cut, by wire EDM, by notch, or by blank notch reblank dies, or by single punch dies known as fine blanking, or through progressive dies. A progressive die is a big die that has several stations in it, and the first station might take the shaft hole out. The second station might take the rotor bar slots out. The third station might take the stator bar slots out, and the fourth station might punch the rotor out of the stator. The next station might shear the ID, what material's left in the ID, to maintain the ID of the stator, and the last station will break the OD of the stator away from the strip of steel that it was stamped out of. It's always advisable to punch the rotor out of the hole of the stator, otherwise you waste it. That's a big cost savings. How do you fasten laminations together to build a core? Rivet, cleat, bond, clamp, interlocking. I didn't put welding up there, but welding has got to be there because that's a very common way. I didn't put it there because I said it before. In-die interlocking of lambs that comes right out of the die. That is a very popular way for high-volume motors. This is an example of a company that makes core stacking equipment. This is conventional cores are made this way through this process for rotors and stators. You can follow it. I'm not going to go over it. But this system, this Mitsui High Tech, that's where they nest the lambs together, and they get cores right off the die. I'll show you a picture of one later. This is what a typical blown-up view of a lamination set would look like. This has 36 semi-open stator slots with round slot bottoms and 40 semi-open rotor slots with round slot problems. This is probably a 4 or 6 pole 10 kilowatt lamination set, and it's very typical of it's very typical of a lamination set used for an induction motor. And this stator lamp could be used for brushless as well. It could be used for reluctant synchronous also. Here's some nice pictures of the interlocking of the lambs that I showed you 2 slides ago from this Mitsui High-Tech. This Max system gives you laminations like this, where right in the die, when you're punching the slots and notches, you punch these little dimples that nest each other from one die to the other and make a beautiful stack that comes right off the die. There's no labor for that. And it's very accurately aligned. Everything is aligned perfect because it was all tooled in the die. This is an example of proper welding of the lamb. That's been TIG or laser welded in those 2 places, and it's important that you do it over holes like that so shrinkage takes place. There might be some stresses from the weld in this area, but it's not going to make the bore out around or put any stresses in most of the magnetic circuit. The flux density when the motor's running is very low or almost zero out in there anyway. Now this is a case where very large cores for wind turbines and power plant generators and great big machines. You see, these lambs have been stacked, the stator lambs have been stacked into groups with spaces between them. And these are special spot welded lamination spacers that provide cooling vents up through the core. And to hold all this together, they put these steel soft straps across the OD, and then they'll have finger plates on the end, another big thick thing on the end, and all this is hand welded together, and this mounts inside of the frame of wherever this machine goes. This is a different way of welding lambs together, and it's done this way to provide these cooling vents, which is very important. We've talked about that before, and we'll talk about it again. And here's an example of a core. This happens to be a motor I designed and built. This is quite a large machine. I don't remember what I think the OD is something like, it's over 200 millimeters. I think it's 200 millimeters, and the ID is 150 millimeters. And it has a lot of slots, and the lambs are quite thin because this is a high-speed induction machine, and it's used for traction for vehicles 12,000 RPM and 4-pole. So these lambs were all bonded together, and it's a very nice uniform core. Excellent tooling was used. And just to show you what it looks like then during the coil insertion process, you can see the slot liners, the cuff slot liners, Nomax slot liners were put in and insulated. And then the coils inserted, and then top sticks put over top of the coils. And we'll talk about those in the lecture on insulating the stator. But when you machine wind the coils and hand insert them like this was done, you can, it's easy to get 35 to 40%. To get over 40%, to get up to 45, you really have to fight the coils to get them in, and a lot of shops don't want to do it, but if the guy works for you, he works direct for you, he can do it. He can get up to 45% slot fill. And what that means is bare copper slot area to slot cross-sectional area. If you're going to automatic machine insertion, wind the coils and insertion with all this fancy tooling induction motors, you can't do that high slot fill. 25-35% is about the max you can get. If you use rectangular wire like Ramey does for the Chevy Volt, you can get 60-75% slot fill. And I'll show you a picture of that. The other thing you can do to increase the slot fill is to use uniquely designed stators. And use fractional slot windings that have the coils wrapped around the individual tooth. Here's a couple of examples. This is actually a sintered, it's not laminated, it's sintered out of powder. and each tooth has its yoke sintered and cast on it with little nesting notches there. And so you can put a bobbin on here, that's what that is, and then layer wind the copper. So you layer wind to get very high slot fill. And let's see, Honda builds their machines like this. There's a lot of different versions of this also, of layer winding the copper around individual teeth. There's lots of ways you can construct a stator to do that. And now there's a number of mechanical considerations that are important to think about for stators. With small stators, you don't run into any of these problems, but large stators, the laminations are going to vibrate, and if you have coils laying down these slots going around the end of the teeth, and if these lambs vibrate, they'll move back and forth like this and cause wear on the insulation and short out the windings. Plus, it makes the motors noisy. So it's not uncommon to use finger plates. These are thick pieces that are kind of shaped like the lamination, but they have a spring effect. There's different designs, and they compress actually from one end to the other to keep all the extending teeth together. Those are called finger plates, and that reduces vibration, noise, and coil insulation wear. Then the next thing that I want to show you are these cooling ducts. Remember I showed you a few slides ago a core that they were welding straps on the OD to hold these sections together. These are stacked sections of lambs that are spaced apart by these stamped ducting pieces, and I'll show pictures of those in another lecture. And that provides, in the rotor and stator, passageways for cooling gases to either air or nitrogen or hydrogen is put through there to see if you have conductors that go all the way down these slots, and so the thermal diffusion paths of those conductors are quite long. So in order to get more direct cooling, these passages allow the cooling gas to go up through the slots and have intimate contact with the portion of the conductors that are going through those openings between the cores. Now the other thing is these big machines that have these big coils that go down through here, the ends are formed in various ways to connect to the next slot, and the mass of those large coils, as you see down here, is considerable. So those will vibrate and work hard in the copper, and then they crack, or you have insulation damage, things like that. So bracing of end turns to withstand vibration, and of course there's magnetic forces on these conductors as well. So it's not uncommon to provide different methods of bracing, and through the course of these lectures I'll point out some other bracing instances as well. Here's one here. Here's a picture of a motor with a big insulated wire cable ring that goes all the way around the core, and so this doesn't support it to the frame, but it does support them all together and keep them from vibrating with respect to each other, because they're hand laced around the coil from the bottom up, and they're laced over. So that lacing to this insulated steel ring here gives tremendous rigidity to this whole end turn mass. Now here's an example of some high performance motors that all of you are familiar with, the Toyota stators. It shows a picture of their motor stator and their generator. This one here, one of these is the Prius and the other one is the Camry. I don't remember which one is which, but these are public pictures. And let's see, I think this one's a Prius and this is a Camry. Yeah, I'm quite certain of that. It shows some of the gears that are in between them. But and here's an example. This is the stator for the 2010 Prius. It's not this one. It's newer. This is 2004. But the 2010 Prius has a core made like that with totally open slots, and the coils are wound on bobbins that fit over the teeth, And half of the coils are taper layer wound, and the other half are parallel taper wound. So you put all the tapered ones in first. Every other one is inserted first. Now you could put the parallel ones in. They'll go in. If they're both tapered or both parallel, they won't fit. But if one is tapered, one is parallel, they all fit and they're balanced. You got the same number of turns in each one of these. The dimensions are such that you have the same amount of copper in each one of them. They're just shaped different, parallel side, taper sided, and it turns out with a 3-phase machine and 12 slots, you've got 12 slots divided by 3 phases. It means there's 4 coils per phase. So 2 of the coils in series are taper wound, the other 2 are parallel wound. It works out that way with every other one. So they're completely balanced windings. Now don't jump off and try this yourself, because Toyota's got this patented. But this is an interesting trick and gives you an idea of how you might configure a stator where it's not, you designed for manufacturing, ease of manufacturing, and for high slot fills both. And it's a beautiful example of that. Now this is a picture of the Ramey stator that uses rectangular wire and has very high slot fill. You see, these are, I think they're square. Whoops, they're square wire, and they're called hairpin windings, and they're inserted in there, and they have very high slot fill, and all these connections are done afterwards. So that's a fantastic design. This is an advanced stator design used for a superconducting machine. And you can see here that you've got these end turn supports. This is a 4-pole machine, so the end turns are huge in this because these are big rectangular wires for high slot fill. So the end turns are big, and all the connections between them took up a lot of space. So all that mass hanging out there vibrating would cause failure. So attached to the stator, here's the stator mechanical part, a big heavy thing, and then these blades that come out here. And they're insulated, of course, and then these end turns are supported with straps that connect to these blades. So that's this is all the cooling stuff in here. But so that's an example of how a core is made. This is the superconducting coils in the rotor. So that concludes this lecture. Thank you very much.